Okay. Yep. Still happens every semester, like the tables creep forward. And at some point, the professor has cornered. Okay. Well, once again, I seem to have very little in the way of notes, but I'm sure my rambling will fill the time anyway. Okay. Well, so first, a last comment about version relations. Okay. So where I proved last time, it's supposed to assume a solution that's this form: u of xt is e to the I kx e to the minus I omega t. Whereas I'd forgotten the minus because I wasn't looking at my notes carefully enough. The growth factors will turn out to be the same no matter how you do it. So having plus or minus is really a matter of notation convention. And it's so important that I adhere to that convention. So I want to make a quick comment about why it is conventional to use a minus when in terms of just technical reasons alone, the plus versus minus doesn't matter just because k is some constant, it's an integer, and omega is something that's related to it. So if I write it this way, e to the I kx minus omega t, thinking it's one exponential, then the idea is that if omega is positive, then this wave function is traveling to the right. So that would be one reason. I don't know what it's a reason. Like I haven't seen it. It's like I found discussion about it online or anything. But I can see why one would choose to define this person relation in terms of having this form of solution with a minus instead of a plus. So now and then certain choices like that are made. And again, it really is just convention. And there may be some reasoning behind it, or sometimes it might be arbitrary. But it's good to know that those kind of conventions are out there. And that sometimes it really is convention as opposed to some more compelling reason like correctness. Okay. Okay. Now, my way again. All right. So now, the main topic of today, I'm going to spend a little time on each of the fundamental PDEs. The PDEs you would have seen in your first course. First, Laplace's equation, heat equation, wave equation. So today it'll be Laplace's equation. Okay. And this very close relative, Poisson's equation. Okay. So I'll write out the more general one. Poisson's equation is a boundary value problem. So we have minus Laplacian of u is equal to f. Here's another example of a convention to put the minus in front. F can be anything. There's no reason not to have a minus over there instead, or not have a minus at all. But it's so that the Laplacian, the operator here, minus Laplacian, has positive eigenvalues. Okay. And this PDE is enforced in some domain omega. And then, and I'll draw a picture here. Here's your generic blob omega. And then we have the boundary of omega, I'll call gamma. But gamma can be decomposed into two pieces. So I'll call this part gamma 1. And so from here to here, and then this part from here to here, I'll call gamma 2. Now, either one of these portions of the boundary might be empty. But the idea is we have different boundary conditions on each portion. So we have u is required to be equal to some given function g on omega 1. So when you specify the value of a solution at a boundary point, that is what's called a Dirichlet boundary condition. And then if you specify instead the normal derivative, it's required that be equal to some given function on omega 2, that is a Neumann boundary condition. And n is the unit normal vector to the boundary. So that'll be equal to this vector over here, but it'll be equal to this vector over here. So depends on the boundary of your domain. By convention, once again, convention that we refer to the outward normal vector as opposed to the inward, which would just negate everything. For a one-dimensional problem in space, so you just have minus uxx equals f, which is a PDE you'll be dealing with often in homework. Then, so I'll just draw one-dimensional case. So your boundary points would be A and B, the endpoints of your interval that defines your spatial domain. So the normal vector would be pointing this way. So normal vector would just be minus 1. It would just be a number, it's for one dimension. And then it would be equal to 1 at the right boundary. So this boundary condition here would translate into minus partial view with respect to x equals something at the left boundary, and then plus partial view with respect to x equals something at the upper boundary. All right. Now, when f is equal to 0, then we call this Laplace's equation. And it's still part of this f equals 0 case. And the solution of Laplace's equation, okay, Dr. Schroeder, is called a harmonic function. That only applies to Laplace's, not Poisson's. Now, it turns out that Laplace's equation or Poisson's equation is relevant to other PDEs that we'll see. This is a time-independent PDE. There's only a spatial domain here, but knowledge of solutions of Poisson or Laplace's equations can be helpful for PDEs that are time-dependent. So I write a heat equation with a source term. So I said UT is equal to Laplacian of U. Oh, wait. Laplacian of U is equal to F. Okay. So what happens is the way this equation behaves, as t goes to infinity, we have du dt going to zero. The solution actually converges to a steady state. That's one of the properties of a heat equation. Not necessarily true for time-dependent PDEs in general. Like, for instance, in the for wave equation, you do not have this kind of behavior. Um, so what that means is U converges to what's called a steady state solution. Even though the solution in general is time dependent, as t goes to infinity, it's going to converge to something. And that would, so if we go back to the PDE, that means you're essentially crossing off the du dt term. Because that part's going to zero. And that steady state solution turns out to satisfy Poisson's equation. Just because you ignore this, and Poisson's equation falls right out. Wherever right-hand side is equal to the source term that you started with. Now your source term may be a function f of xt, it may be time dependent as well, and we're assuming that f of xt as t goes to infinity also converges to a steady state. So that's one thing to keep in mind here. If f happens to be 0, or if f goes to 0 as t goes to infinity, then we're left with a Laplace's equation. So we can say that the steady state solution of a heat equation in that case is a harmonic function. So it's a typical thing to, when you're dealing with a time-dependent PDE, to ask yourself, well, what does a steady state solution look like, or is there a steady state solution? So you're just assuming that any time derivatives are 0 and see what you get. That contributes to your understanding of the solution of the original problem, that converging to something. Okay. Questions so far? I'm looking at the board on a meeting here, and there's some troublesome glare right in this area. I don't know if there's anything that can easily be done about that. Well, I don't know if the blinds can be lowered or prevented. What? Sorry, what? Oh. Okay. Oh, okay. Because like on the screen, I can still see it. Yeah. Yeah.
Here it's more. Here it's less. A lot less.
Okay. So, yeah, because here the screen is big, just glare on the video.
See here, it's all theirs.
Oh, okay. Okay. No. Yeah, because I don't know if I were to pull those blinds down, if that makes a difference. But again, people might not like that. Oh. Okay, maybe I should just avoid that part of the board. Let's see. Can I? Oh yeah, I can. I'll shift everything to the left. Okay. Actually, what I'm gonna do is I'm gonna draw a line here before I continue. Okay. So right here where it starts to become unreadable. Okay, I think that'll work. Okay, so now that my writing domain has been defined, um, So what we'll do now, my goal is to find what is called the fundamental solution of Laplace's equation. Okay. And what this will let me do is, so fundamental solutions in general, what they allow you to do, I'm not going to give a formal definition at this point, but it's the solution of a certain special case of the original PDE with a specific right-hand side, and based on what's called the Dirac delta function, which I'll discuss a little bit later. And what it allows you to do, if you know a fundamental solution, that lets you define solutions of a PDE in general for whatever problem data you have. And there are numerical methods based on fundamental solutions. For example, our own Dr. Chen, part of his work is called the method of proximate fundamental solutions. So in his methods, numerical solutions are obtained from knowledge of at least approximate fundamental solutions of the underlying PDE. So even though I'm not really going to get into numerics today, just keep in mind that while this discussion is mainly theoretical, these do play a role in some numerical methods. Okay, so one of the aspects of a fundamental solution is that it is a free space problem. So our domain omega is at the whole of Rn. The nice thing about that is we have no boundary conditions to consider. We can focus just on the PDE itself. Okay. I'm also going to assume that my solution, u of x, is some function that depends only on the variable r, which is the radial variable. So for a formal definition, r is the square root of x1 squared plus the sum squared of all the coordinates of your point x in n-dimensional space. So if we were in 2 dimensions, it'd be the r from polar coordinates. If this is 3 dimensions, it'd be a variable often referred to as rho from spherical coordinates and so on. So another way of describing it is we assume that our solution has radial symmetry. Okay. To mention, this is often written as absolute value of x when x is a vector. Absolute value bars often are used to refer to the Euclidean length. Also often written using the double bar, indicating a norm of x. Sometimes with a subscript 2 to make clear that it's referring to Euclidean length as opposed to some other norm.
Since it's excluding 0.
Oh, okay. Something is weird here because, yeah, domain is specified to be all of Rn. Okay, 1 second here. Oh, actually, whereas the final answer is defined on all of Rn except for the origin. Then you think that would be the domain too. Okay. May have to go back to the original MIT notes about that. You say your domain to be Rn excluding the origin. You can argue that the origin is supposed to be a boundary point.
In the next.
Yeah, yeah, I know.
But is it the same interpretation?
Like, my quandary is, I feel like it should be consistent. Yeah. Okay. Because the final result that we're going to get is not necessarily defined, actually, most of the times is not defined at the origin. Okay. And I could easily say, okay, I should fix this to say it's Rn except for the origin, but then I feel like that contradicts the statement with no boundary conditions because you can think of the origin as being a boundary point. Okay. You know what? I'm going to. No. Rigor is important. Okay, I'm gonna look something up here. I'm going to refer to my primary source. Okay. Okay. Huh. Yeah, the original notes have this, yeah, the same issue. Declare omega to be all of Rn, specify no boundary conditions, really symmetric solution in Rn minus the origin. So, there seems to be something missing here. And, okay. All right, so probably the best way to deal with this, although I'm not happy about this, uh, about my course of action. What I may have to do is look this up elsewhere later. Is amend the domain here to be Rn excluding the order. Because the solution will, in most cases, be undefined, turn out to be undefined at the origin. So now I can say radial symmetry in omega. Now it matches what's in the notes because now omega is this. So, or is this. Okay. So just still going for the no boundary conditions line, despite my discomfort about that. So, okay. All right. So now what we need to do is this Laplacian in Cartesian coordinates is the sum of all second partial derivatives, rather with respect to the same variable twice. But to account for radial symmetry, we need to express this in radial coordinates. So we need to, so if I have R defined this way, then I need to make a change of variable to express the Laplacian in terms of a radial coordinates. So if I have partial derivative of R with respect to xi using this formula over here, so that's going to be 1/2 sum of squares minus 1/2 times 2xi. So now I can simplify that. 2's cancel. I end up with xi over r. What I really need, of course, is the second derivative. Okay. So now I'm just going to take the derivative of this with respect to xi using the quotient rule. That's going to be r times derivative of xi, which is 1, minus xi times the derivative of r with respect to xi, but that is xi over r again, all over r squared. So we get 1 over r minus xi over xi squared over r cubed. Okay. Now, this allows me to express derivatives of u with respect to xi in terms of accounting for radial symmetry. So uxi, so that's equal to dv dr, actually I'll write it this way, so it's easier to see, dv dr times partial of r with respect to xi. That's just by chain rule. But now what I really need is a second derivative. So I'm going to differentiate this whole thing with respect to xi. So that's going to be equal to, so I take the derivative, this is going to call for product rule. So I'm going to have second derivative of v with respect to r, which will enter, and then partial of r with respect to xi, but I already have one of these here. So now I'm going to have partial of r with respect to xi squared, okay, plus dv dr, and now I can take a derivative of this with respect to xi, but that's just the second derivative. And now all these partial derivatives of r with respect to xi, I can fill in what they are. Now I have v double prime of r times this squared, xi squared over r squared, plus v prime of r times the second derivative So that is my, so that's each second partial derivative of u with respect to xi twice. Any questions about how this was arrived at? Now, the Laplacian is the sum of all of these second partial derivatives with respect to xi twice. So I'm going to add up all of these from I equals 1 to n, and that's my Laplacian. So let's see what we get by doing that. Well, sorry, what?
Could you leave it out?
This part?
Yes,
I'm leaving it there anyway.
I'm just
Okay.
working it out.
Okay, please let me know when I'm able to continue. I'm still gonna leave that up, but I don't want to erase anything else.
I'm just in the product.
Okay. All right, yeah, please stop me sooner rather than later, because otherwise I don't know. Okay,
I just-
oh, I just realized that I erased something and I'd like. This felt needed. Okay, so we have R square root of. Okay. So now the Laplacian of U, that's the sum of all these second partial derivatives. So I'm gonna add up all of these. So I have V double prime R X I squared over R squared plus V prime. Okay. Now, using and some all this little summation. So using various properties of summation, linearity, I have V double prime R over R squared sum of xi squared plus I have from R over R times the sum of 1. And I have minus B prime of R over R cubed sum of psi squared. But the sum of xi squared is R squared. So we have a lot of simplification here. So we end up with this part collapses to this V double prime of R. And then over here we have V prime of R, well, the sum of 1, that's just n. So now I have n minus, n minus 1 over R times V prime of R, because here I have R squared over R cubed, so that gives me 1 over R. I also have 1 over R here. So V prime of R over R is a common factor in all this part times n minus 1. So we see that the ODE now that we have actually depends on the number of spatial dimensions because of to end there. So we're going to get a different solution for each choice of n. So now I have a second order ODE for V. But look at how V is involved. I have V double prime and V prime. I don't have V by itself. No derivative. So our original equation, Laplace U equals 0, is a first order separable actually also linear, ODE in V prime of R. So I'm going to let W equal V prime. So really what I have is W prime is equal to 1 minus n over R W. That just comes from taking this part and moving it to the other side. So this is the ODE I now need to solve. Now, anytime you have an ODE, like W prime equals some function of your independent variable times your solution W, there's a general solution formula for that that is good to know. So W is equal to some arbitrary constant, which I'll call B, times e to the integral of this function that's multiplying W. So 1 minus n over R dr. So, but now what I want to do, well, first, any questions up to this point? All right. Now, so what I need to do is I should evaluate the integral. 1 minus n is a constant. I'll pull that out. And I have 1 over r dr, but it's natural log of r. And then if I use the properties of logs, I can write that as b e to the natural log of r to the 1 minus n. So the factor multiplying the log, I can move that up here as an exponent. And now I have e to the log of something, which lets me do what?
Sorry. The thing inside the log. R to the power.
Yeah, the exponential and log function cancel. Yes. The inverse function. Yeah, so b r to the 1 minus n. So that is my b prime of r. So I'm almost there. I just need to integrate this to get the v of r, and then I can write that in terms of x at the end. So for example, if n is, so now we have 3 scenarios. First scenario is n equal 1. All I have there is I have r to the 0, so I just have the constant b. So if your derivative is a constant, then your function is linear. So it's br plus c, where b and c are as yet unknown constants. That's all it is in the n equal 1 case. For n equals 2, I have b over r, this is b to the 1 minus r to the 1 minus 2, so r to the minus 1. So integrate that, and you get natural log. I have b natural log of r plus some constant of integration. And then for all other n, so n greater than or equal to 3, we'll have some more negative power of r. And so for integrating, that's just a power rule. And I'm glossing over the constant factors in the power rule. The point is it's going to be, because you're going to increase the power by 1, so r to the 2 minus n. I mean, you're dividing by 2 minus n, but I'm going to gloss over that part. The point, because we have arbitrary constants anyway, so you have some constant b over r to the n minus 2 plus the constant of integration. So those are the possibilities for your v of r. All right, questions about how this is obtained? All right. I don't know if I'm okay. All right. If you're showing your papers, I can't tell if you're writing to pause or not. Okay. All right. So now I'm in a position to write down the fundamental solution of the Laplace equation in all of n space except for the origin by choosing values for b and c. Because for any b and c, you have something that satisfies Laplace's equation in all n-dimensional space. Okay. I'll call that L5x. So for n equals 1, it is minus 1/2 magnitude of x is 2 minus 1 over 2 pi natural log of magnitude of x, and then for all other n, n minus 2 alpha of n, which I'll define in a moment, times 1 over magnitude of x to the n minus 2. Alpha of n, that equals the volume of a unit ball. In other words, all points x where the magnitude is less or equal to 1 in Rn. So for instance, in the case of n equals 3, you'd have the sphere be not just the boundary, but the interior, the volume of that. So in other words, what is it, the 4/3 pi r cubed? Yeah. Okay. Now, as far as the constant factors, I set C equals 0 in all 3 cases, but I made these seemingly odd choices for B. The constants are chosen so that the integral over all of Rn of minus Laplacian of phi is equal to 1. So what's interesting is even though the functions themselves are not like, well, except for the case of n equals 1, are not defined at the origin. But the but here I'm integrating over all of Rn. Okay. So another way of looking at it is that as phi is a solution of this PDE, minus the Laplacian of phi equal to delta of x, where delta of x is known as the Dirac delta function. Although it's not, technically speaking, it's not a function, it's called a distribution. So properties of a Dirac delta function that are of importance to us is delta x is equal to 0 for all non-zero x. So sure enough, if we consider the domain Rn minus the origin, this is equal to 0 in that domain. So we have satisfied Laplace's equation in that domain when the origin is excluded. It's not actually, the value is not actually stated at x equals 0. That takes me to the other property, is that the integral over all of Rn of delta x dx is equal to 1. And forming its central function as a distribution, that the integral over all of Rn of f of y delta of x minus y dx is equal to f of y. So it's a way of selecting the value of f at a particular point, because for all x not equal to y, this is going to be 0. Informally, you can think of the delta function as a function that, okay, 0 everywhere, but it is you think of it as an infinite spike at the origin. Or if you think about it as a function where the area under the curve, yes.
With infinite and infinitesimal rate.
Yeah, so that takes me to my next point. Suppose you have a function that has area under the curve equal to 1, and you make it thinner and higher, and then they take a limit of that process as it goes to infinite height, infinitely small width. You can think of that as approximating what the delta function does, to have this effect. I had a professor at Stanford who would talk about the delta function, and he was the first one to tell us that it's not really a function, it's a distribution. And he tried to describe it by making an analogy with the character Voom from Cat in the Hat. Because it was never described what Voom is, only what Voom does. It cleans everything up. So that was the extent of our understanding of the delta function. Okay. Well, I'm curious, and I may not have time to look into it right here, is if I were to take any one of these solutions and try to evaluate this integral over all of Rn, because this is supposed to be, if I take a Laplacian of this for all non-zero x, it's supposed to be 0, but not defined at the origin. So, all right, if time permits, I might look at that. Okay. So, maybe we could in polar coordinates or something. All right. Do you have any questions up to this point before I reach the conclusion? Because I could use this property right here, to tell you what the fundamental solution of Poisson's equation is on all of our end. Okay. So, the Laplace of u is equal to f on Rn, so no boundary conditions. Is u of x is the integral over all of Rn of the fundamental solution of Laplace's equation evaluated at x minus y, f of y dy. And to see why that's true, I take minus Laplacian of both sides. So my Laplacian is going to be with respect to x. So I have minus Laplacian of phi x minus y, f of y, y. But this is the delta function of x minus y. So it amounts to a convolution and that gives me f of x, which is what I would expect. That minus Laplacian of u equals f. And this can be written as delta convolution with f, convolution of the two. Another term for fundamental solution known as a Green's function. So Green's function is very useful for finding solutions of general PDEs in terms of these fundamental solutions. So this is a Green's function for Poisson's equation. Similar thinking applies to other PDEs, like the fundamental solution of, say, the heat equation. You're solving PDE, but the heat equation is equal to, instead of equal to like ut minus uxx, or Laplacian of u, is equal not to 0, but to the delta function. And it lets you describe such the more general solutions of a heat equation with whatever like initial data you have. Same thing for the wave equation. Um, One thing I thought about when I was first learning about Green's functions and how they come solving a PDE, differential operator times u is equal to the delta functions. Um, the delta function of x minus y is equal to 0 unless x is equal to y. It kind of reminds me of the identity matrix. The identity matrix has all entries, ij equal to 0, except when I is equal to j. You can almost think of the PDE for fundamental solution. PDE applied to u is equal to delta function as defining an inverse matrix of sorts. And then if you think of your PDE as canonical system linear equations, the AX equals B problem, well, what is the solution to that? X is equal to A inverse B. So you get the solution of your PDE by applying your inverse matrix, which is the fundamental solution, as a function of x minus y, rather than just x, to your right-hand side. So there's an interesting parallel between fundamental solutions of Green's functions and for linear PDEs at least, and solving a system of linear equations and thinking in terms of a matrix inverse. So books never talk about that. I guess it's not something we want to get into, but I feel like having that intuitive understanding is helpful. And I always like to see relationships between ideas from very different areas of math. And besides, math is the art of reducing all problems to linear algebra, so why not? Okay. So questions about this way of solving Poisson's equation?
The thing that your del x minus y,
Yeah.
it just looked like it was writing it, and I just spent like
Oh,
minutes going bit crazy.
okay.
But it's okay.
Yeah, I'll make that clear. Yeah. Whoops, yeah. Okay. Also had a situation during the class I was substituting for Stanford. I was, in my notation, I was using a lot of lowercase q's and also lowercase a's. And I got to the very end of presenting all this for 20 minutes or so, and then the student pointed out that they couldn't tell the difference between the a's and the q's. So in the future, when I would cover that, I would exaggerate to make sure that there was no ambiguity. Okay. All right. Has anyone looked at the first homework problem? Okay. And how did that, okay, so,
Yes, but it-
okay. All right. Hope that continues. Okay. All right, since there's still some time left, what I'm going to try doing here, just to see what would happen, because I haven't done it before. I can take a fundamental solution for 2 dimensions and see if I get anything meaningful when I try to integrate that over all of R2. Because presumably I should get 1 based on the way that it's scaled. So for n equal 2, fundamental solution minus 1 over 2 pi natural log of square root of x squared plus y squared. Okay. So then, so phi x would be minus 1 over 2 pi actually, I'll write it this way. Minus 1 over 4 pi natural log of to not have a square root to deal with. Okay, so I'm gonna have 4 pi over x squared, plus y squared times 2x. Okay, and then y would be similar, and then phi xx. Okay, this is where things are gonna get a little ugly. So. Oh, not so bad. That would be y squared minus x squared. Okay. And all I'd have to do is reverse the roles of x and y. Oh, wait a minute, though. I'm just gonna get 0. Well, except, although, okay, yeah, so for all x not equal to 0, I am gonna get 0. But it doesn't matter if what happens to this as, x and y go to 0. Like, as x and y go to 0, this is going to 0, that's going to 0. Okay. And if I write these in polar coordinates, that's r squared sine squared theta, r squared cosine squared theta, all over r squared. And that simplifies to sine squared theta minus cosine squared theta. Okay, which well, the convenient thing about that is oh yeah, but there's different ways of writing this. Actually, I think this is like minus cosine of 2 theta. Yeah. Okay. But then,
It's actually cosine squared 2 theta over 2.
oh, wait. Oh.
Sorry, cos 2 theta over 2.
Oh, yeah, I forgot about that. Okay. Minus or no minus? Okay. That's strange. Okay.
There is a line.
Yeah,
There is a. I wrote the 2 cos squared.
I remember that. Okay. I'm still not sure about the 1/2 either.
So I had cos 2 theta has to have 2 cos squared theta minus 1 and 2 sine squared theta. So if I add them both, we get sine squared theta minus cos squared theta. 2 is the common factor equals cos 2 theta.
Using a half angle formula. Okay, but 1/2 cancel out. I have 1/2, one, yeah,
Okay, you're right.
told ya.
I'm sorry.
Okay. I don't remember all the trick I did in these, I remember that one. But,
I'll try to do better.
okay. And then if I was gonna integrate this, I'd also have, the effect of r for change of variable to polar coordinates, but the other one's gonna, okay, so here I end up having cosine 2 theta over 2 pi, and then partial respect to y is gonna be minus that, it's all gonna cancel out, so. Okay, this didn't go like I hoped, but it's gonna be recorded anyway. Dang it. Okay, maybe I'll look it up somewhere. It's fun to try. Okay. All right. Okay, it's almost time to end anyway. Yes.
The second derivative. I
Yeah.
don't know if you would like to check the numerator. The y squared minus x squared. We're not supposed to y minus x.
Oh, wait a minute. Oh, there is something I did forget though. That's supposed to be squared.
Yeah. Okay.
Oh, is that what you're talking about?
Yeah.
Okay, yeah.
But it doesn't make.
Yeah, so still a problem at the origin. Okay. And then when I multiply that by r, okay. So we still have it 0 for away from the origin. But then you have difficulty with the integral at the origin. So, okay. All right. Still unable to conclude it, but at least what's on the board is correct. If incomplete. All right. Well, if I find something out about this, I can mention it for next class. Okay. Until next time.